Hello again. This is Math204, and now we're starting Chapter 2, which is complex functions. So in the last sections we learned about complex numbers themselves and all the various algebraic properties, and we learned a little bit about some more analytic stuff with open sets. But for this chapter we get into it much more. So section 2.1, functions of a complex variable. We've seen lots of functions already, and I've been using the function notation previously in class. Very roughly, you know what functions from the real line into the real line look like, and you know that for some subset of the real line you can define functions from that subset into the real line, and you know about things like the domain of the function, and you know about the range of the function, and in class with Glenn you may have heard about the codomain of the function, which is some people call it the target set. What's the difference? Well, the range is everything that f of x can get to. The codomain is the set into which the function maps. Right, so everything that you know about functions of a real number apply to functions of a set, and when you eventually get to the more abstract definition of a function, you'll see that everything makes perfect sense. So there's lots of examples, and you can invent all sorts of things yourself, but you've seen many examples in class already. The real part of the complex numbers maps into the real numbers. And similarly, the imaginary part of a complex number maps into the real numbers. The modulus function takes the complex numbers into the real numbers. The argument takes the complex numbers into, well, as you've seen it so far, the argument is not a function, because argument of z is only an element of a set, which would be the principal argument of z plus 2 lots of pi times k, where k is inside the complex numbers. So does not have a unique value. So not a function. There are ways to make it a function. So you let the target set be the set of all subsets of this form, and then of course the argument would pick out one of those subsets. Alright. A function that takes, say, the function that takes z into z squared is a function, takes complex numbers to complex numbers, and complex conjugation, the thing that takes z and spits out its complex conjugate, is also a function. So you've seen lots of them before. Right. So as I said, the domain of a function, which I was writing the whole word out, and I'm really just going to write the domain of f, or maybe even in lowercase, the dom of f, is the subset of all complex numbers so that f of z is defined. Here's another example. What about the function that takes a complex number into 1 over complex numbers? Right, it's not defined at 0, but otherwise it is. So the domain of this function is the complex numbers minus the origin. Actually, the definition. So if I want to be very proper, let f be a function of a complex variable. So it goes from some subset of the complex numbers into some subset of the complex numbers. Then the range of f, which is sometimes written with a lowercase f, is all values that the function can take when z is an element of its domain. Right, and you know, you've seen this notation. F goes from, so the function goes from one set to another set. Another way to write this is that the function takes an element and spits out some function of it, like exp iz, for example. And this can be read as takes, as I said. The function f takes z into this. Sometimes also you'll see it written with the function above as well. This is just specifying the rule without necessarily having to specify the label for the rule. That's all. You have seen periodic functions. Periodicity. Function f of a complex variable is periodic if there exists p, an element of the complex numbers. P has to be non-zero, so that f of z plus p is equal to f of z. So you've seen one of these before. The function r into the complex numbers, given by f of theta equals ei theta, is periodic, and that is shown by and of course, because cos and sine are periodic with 2 pi, this is ei theta, which equals f of theta. So periodic functions are important, and it's worth being aware of that definition and keeping it in mind. Sorry, just organising my notes here slightly. That definition for periodicity works just as well for real numbers as well. It's just that we're dealing with complex numbers, so, and for other types of sets also. Okay, alright, now when we've previously been given a function from the real numbers to the real numbers, for example, x goes to x squared, we could draw that. Take two copies of the real numbers, there's one, there's another, and we can draw its value. F of 0 is 0. F of 1 is, well, that's 1. F of 2 is, well, that's 4. We can draw it. And it gives a nice way to visualize the function. Now let's consider f of, right, and now this thing is you can think of it as two-dimensional because each number has two bits, its real and imaginary parts. So if we wanted to do the same thing, we would have to take one copy of C, and then we would have to take a second copy of C, except I'm not doing a great job. Where do they intersect? I don't know, and my angles are all wrong, and well, it's all just a giant mess. The point is, anyway, whatever we drew, drew, would need to be four-dimensional. This is two-dimensional. One-dimensional space, one-dimensional space, and the graph will be two-dimensional. Two-dimensional space, two-dimensional space, and the graph will be four-dimensional. Now, drawing a I'm working with a piece of paper, so I would need to draw a 4D space on a 2D piece of paper, and I know I can't do that. You might be more clever than I am, but no. I think the best way to say that is, I can't even. So the way that most people attempt to visualize these things is to draw a copy of C and draw a second copy of C and consider how lines and circles in one copy get transformed into lines and circles in the other copy. So here's an example. We take a function from the complex numbers into the complex numbers, and we will define it by f of z equals 1 over z. I'm going to call this the z plane, and I'm going to call this one over here the w plane. So this is equal to w, and so f of z, which I'm going to write x plus iy, 1 over x plus iy, is equal to w, which I'm also going to write as u plus iv. So let's unpack this a little further. Right, using the normal techniques, which equals u plus iv. So this implies that u is equal to x over x squared plus y squared, and v is equal to minus y over x squared plus y squared, which is a little odd, or at least you'll see it has interesting consequences. So the first thing to try is maybe to see what happens to the real lines. So or perhaps even just some points. Let's do some points first. So z is equal to 1. That implies that x is equal to 1 and y is equal to 0, which implies that u is equal to 1 and v is equal to 0. So there's 1, and that gets mapped to 1. Great. Z equal to minus 1. X equals minus 1. Y equals 0. And that implies that u is equal to minus 1 and v is equal to 0. So there's my minus 1. Those 2 points get mapped onto each other. Great. Z equal to I. This implies that x is equal to 0 and y is equal to 1. And that gets mapped to u equals to 0 and v equals to minus 1. So there's I, and that's the same as saying that w is equal to minus I. So there's minus I. So so maybe there's some kind of flipping happening. Okay, z equal to minus I. I'll spare you all the details. U equals 0, y equals 1, v equals 1, w equals I. So maybe there's some flipping. So real line question mark, but we know that the ones are fixed. Imaginary, maybe it's flipped. Don't know. More investigation. Okay, so let's draw a little table. Now I'm going to be a little clever because I know that we're taking the inverses of things, and I know that inverses of things kind of shift infinity to 0 and 0 to infinity. So let's say z well, let's do just the real line first. Real line. So we have x over here because y will always be 0, and because y is always 0, we know v will always be 0, so we just have u over here. So when x is less than 1, then, let me write this down, u equals x squared plus y squared, which for y equals 0 will be 1 over x. So this is, so I'm thinking about this minus 1, I'm thinking about everything here, and that gets mapped into everything here. So it's like the infinity bit gets put in there, and we know that for numbers that are very large, they get made very small. So we say f of large, and this must be f of small. And that makes sense, because this function is probably continuous once we tell you what continuous means, and we know that minus 1 is a fixed point. So we know that minus 1 is a fixed point, so that's that. And this is fairly easy to see as well. So that means that this bit here gets mapped into this bit over here, just the same way as before. So remember that z mapping to 1 over z, the domain of our function f is z minus the origin. So we don't have the origin in there. So the bit between minus 1 and the origin gets mapped to the large numbers, and the large numbers gets mapped to the bit between minus 1 and 0. And the same thing happens for the positive portion. Now we can have a look at what happens to the imaginary line. So in this case we have x plus I y. Well, we've got no x because we're all just dealing with imaginary bits. Gets mapped to 1 over y. Excuse me. Right, so let's have a look at the imaginary line. So in this case, x plus iy, but there's no x because we're just imaginary. This is 1 over iy, and that will be equal to minus I over y. Great. So we can work this out. Right. So this means that y goes to minus 1y, which is the v from before. So here we have y, and here we have v, and it's basically the same as this, but notice there's a sign change. So the sign change flips. Right, I goes to minus I and vice versa. So if we have y less than minus 1, then we have the same thing occurs as for the real line case, but because of the minus sign, we get a little bit of flip. So this bit here gets mapped to this bit here. So the positive portion between 0 and 1 gets mapped to everything less than minus I on the imaginary line, because we don't have the ordering that we have available to us normally. Right, and everything works the same way, but with the flip. So, so this portion here gets mapped to this portion here. So it's kind of like the outside gets mapped to everything with modulus bigger than 1 gets mapped to everything with modulus smaller than 1, and there's also a flip in the real line. We can check that by looking at the circle. So it said the complex numbers be such that the modulus equals 1. So that's the same as saying that x squared plus y squared equals 1. And f of z, right, f z is equal to x plus iy, of course. So f of z is equal to 1 over z, which we know is x minus iy over x squared plus y squared, and we know that that is equal to 1, so this is z bar, and we know that that is reflection in the real line. So the way to think about this is, here's our line. I'm going to draw this bit on the bottom with dots, and I'll put this bit here in a solid line. Remember, we don't have the origin. Everything outside, don't have the origin. Solid line underneath, dotted line on top, and everything outside, modulus greater than 1, gets mapped to things that have modulus less than 1, and the positive hemisphere of the units in the complex number gets mapped to the negative hemisphere, z 1 over z. Great, and you can check this in even more detail and keep checking things. And it's worth continuing to explore and understand what happens, because this is not the full story, really. So as an example, so this is the line given by the real part of z equals 1. So 1 over 1 plus iy is equal to 1 minus iy over 1 plus y squared. So that says that u is equal to 1 over 1 plus y squared, and v is equal to minus y over 1 plus y squared. So of course, that's the number 1, and we know that the number 1 gets mapped to itself. Now, what is this? This is a little bit awkward, but it is possible to show that if u and v satisfy these relations, then u minus 1/2 squared plus v squared equals 1/4. How did I get there? I noticed that u squared plus v squared is equal to 1 plus y squared over 1 plus y squared squared, which is 1 plus 1 over 1 plus y squared equals u, and then complete the square to work out this. So the image of the line r equals 1 is a circle, and that circle has center 1/2, and its radius is 1/2. So there's a lot of very interesting things, and it is hard to visualize these functions because you're working with two-dimensional things mapping into two-dimensional things, which makes it awkward. So you can play a lot of games with trying to draw complex functions for a long time, and it's worthwhile because those transformations of a complex plane can be very, very important, particularly when it comes to solving certain types of differential equations.